A liquid goes in, a thread comes out. The thread is made of diamond. It is thinner than DNA, and it may be the strongest one-dimensional material we have ever made. The entire global supply of it, everything ever synthesized by every research lab on Earth, would barely fill a teaspoon. And yet it has a name, a confirmed structure. It has been made, it is real, not a computer simulation, not a theoretical prediction, not a hopeful extrapolation from something adjacent. A real material made by real scientists in real laboratories that has been characterized and confirmed and published and peer-reviewed. We just cannot use it. Yet. Not because it is weak, not because the science is wrong. Because of three problems that have nothing to do with the material itself, you cannot make enough of it. The pressure required does not exist outside a laboratory. And solving both of those would not matter because the third problem is stranger than either. That is not a funding problem. It is not a science problem. It is something stranger than both. This is the story of diamond nanothreads. And it is really the story of why the hardest problem in material science is not discovery anymore. To understand why this matters, you need to understand what we have already tried. Carbon nanotubes, the 1990s. Experimental strengths were measured in the range of 11 to 63 gigapascals, up to 50 times stronger than structural steel. Researchers talked about cables strong enough to reach orbit, body armor that stops rifle rounds, aircraft fuselages lighter than anything we could build. That was 30 years ago. You do not own anything made of carbon nanotubes. Now there is something with numbers that in some theoretical models exceed even nanotubes. Diamond nanothreads. And the scientific community is genuinely excited. If diamond nanothreads could match or exceed everything we currently build with, why has not a single one of them replaced anything? To understand what makes diamond nanothreads unusual, you need one piece of carbon chemistry. Just one. Carbon bonds to itself in different ways depending on conditions. In graphite, the stuff in your pencil, carbon atoms form flat sheets that slide past each other. That's why graphite is slippery. In graphene, you isolate one of those sheets. Single atom thick. Extraordinarily strong. Roll that sheet into a tube and you get a carbon nanotube. Hollow. Incredibly stiff, one of the strongest structures ever synthesized, at least on paper. Now here's the key. Take that nanotube and fill it in. In diamond, carbon bonds to 4 neighbors instead of 3, a rigid 3-dimensional lattice in every direction. That's why diamond is the hardest natural material we know. A diamond nanothread applies that same bonding at the smallest possible scale. Not a hollow tube, a solid rod. Every atom inside is structurally active. Think of it this way. A carbon nanotube is a drinking straw. A diamond nanothread is a solid metal rod of the same diameter. Same size. But every cubic angstrom of space inside is doing work. This matters more than it sounds. In a hollow tube, when you apply force, only the walls carry it. The interior is dead space, structurally inert. As the tube gets thinner, the ratio of wall to interior gets worse. At the nanoscale, you're mostly carrying air. In a solid rod, there is no dead space. The load distributes through the entire cross-section. Every bond contributes. And when every bond is diamond strength, sp3 carbon, the numbers that fall out of the math are almost difficult to believe. That's why the theoretical numbers are so extraordinary. And it's why making one requires conditions that border on the impossible. So why did it take until 2014 to make one? The answer starts with benzene, a clear liquid, 6 carbon atoms in a ring. Completely unremarkable under normal conditions. To make diamond nanothreads, you trap benzene between 2 industrial diamonds and crush it. The instrument is called a diamond anvil cell, and the pressure it generates is planetary. For this classic benzene route, 15 to 25 gigapascals. The deepest point in the ocean is 0.1 gigapascal. Heavy industry presses reach maybe 1 gigapascal. This is 200 to 2,000 times beyond either the pressure found deep inside a planet's mantle. It is one of the more quietly absurd pieces of scientific equipment ever built. using the hardest natural material on Earth to create something resembling the hardest natural material on Earth. Under that pressure, benzene molecules are forced so close together they begin to react. The carbon rings link into chains, the bonding transforms from flat graphene-style bonding into diamond bonding. The chains don't just connect, they become something different. What comes out is a bundle of threads, each one a sequence of carbon atoms bonded like diamond, extending in one direction. Micrograms of material, invisible to the naked eye, real. The 2014 paper from Penn State was the landmark result, the first time structural conformation was solid enough to stand up to scrutiny. Since then, research groups in China, Germany and Australia have contributed significantly to mapping structural variants and exploring alternative routes. Before we get to what's stopping it, it's worth understanding what we'd actually do with it, because the applications aren't abstract. Start with body armour. Current hard armour uses ceramic plates backed by Kevlar. It works. It's also heavy. A full plate carrier can weigh 20 to 30 pounds. With a material that has diamond nano threads projected strength to weight ratio, you could theoretically build armour that stops the same rounds at a fraction of the weight. Light enough that it changes what's possible in the field. Consider medicine. The instruments surgeons use inside the human body are constrained by what materials can do at small scales. A fibre with diamond nano threads' theoretical properties would be stronger than surgical steel, while a fraction of the diameter, small enough to go places current instruments can't reach, and strong enough to bear load when it gets there. Medicine could change. Then there's aerospace. Every kilogram you strip from a launch vehicle is a kilogram of fuel you do not have to burn. The structural components of a rocket are already engineered to the limits of what carbon fibre composites can do. Diamond nano threads' theoretical properties could reopen that design space entirely. Aerospace designs could look very different. And then there's the one that gets materials scientists animated, the space elevator. A cable anchored to the equator, extending 36,000 kilometers to a counterweight in geostationary orbit. Climb the cable instead of launching a rocket. Getting 1 kilogram to low Earth orbit costs roughly $2,000 on the most efficient rockets available. A space elevator could cut that to tens of dollars. The reason it does not exist is not engineering, it is materials. No material we currently have is strong enough to build a cable that long without collapsing under its own weight. Diamond nano threads at their theoretical strength would be. The material would qualify. The problem is we cannot make it. That is what is at stake. Not better phone screens, not slightly lighter bicycle frames, the space elevator. Armour that soldiers can actually wear for a full day. Surgery that goes places current medicine cannot. A new era of aerospace. Those are the applications waiting on the other side of 3 unsolved problems. The material exists, the need exists, the gap between them is the story. So if we can make it and it's theoretically this strong, what exactly is stopping us? 2 conversations are happening about diamond nano threads. They sound like the same conversation. They are not. Theoretical strength is calculated from first principles, from the known properties of sp3 carbon bonds, the geometry of the structure, and computational models of how the lattice would respond to force. The models are sophisticated and they're genuinely informative, but they describe an ideal structure, perfectly ordered with no defects, infinite length tested in isolation. Some models propose tensile strength values in the range of 50 to over 100 gigapascals, comparable to or exceeding carbon nanotubes. Structural steel is around 0.4 gigapascals, so that gap is difficult to overstate. The strongest material we may have ever made has never actually been tested for strength. Think about what that means. No one has taken a diamond nano thread, applied force, and measured when it breaks. We have not pulled one until it fails. The figures you've heard, 50 to over 100 gigapascals, come from models, from calculations, from theory. We don't know how strong it actually is because we've never had enough of it to find out. What we have are spectroscopic signatures that confirm the bonding structure is sp3 carbon, consistent with diamond-like bonding. We have X-ray patterns that confirm some degree of long-range order. We have computational predictions based on those confirmed structures, and we have comparisons to other carbon materials with known properties. The theoretical case is genuinely strong, but it is theoretical, and that gap between what we predict and what we've confirmed points to the larger problem, not a problem with the material, but a problem with everything that comes after it. There are three problems, each one independent, each one enough on its own to stop a material cold. Right now, diamond nanothreads can only be made in quantities measured in micrograms, millionths of a gram, in a laboratory using equipment that requires tremendous skill to operate. Consider the scale. A standard carbon fibre bicycle frame contains roughly 1 to 2 kilograms of carbon fibre. The total quantity of diamond nanothreads ever synthesized by the global scientific community is vanishingly small by any practical measure. The synthesis process is inherently batch limited. You load the cell, compress, wait, decompress, extract. Each run produces a tiny sample. You cannot run the machine faster. You cannot build more machines and linearly scale output because the geometry is constrained by the diamond tips, which are limited by the economics of producing gem-quality single crystal diamonds of sufficient size. There is no continuous version of this process, no furnace running day and night. You are creating pressure conditions that briefly transform the feedstock, then releasing, then starting again. This is not a problem engineers have already solved. It is a fundamental constraint on the current synthesis pathway. Which brings us to the pressure problem. Those 15 to 25 gigapascals are beyond anything industry can generate at meaningful scale. You can achieve this with diamond anvil cells, but not with steel machinery. Steel would fail, not with large volumes. The engineering required to contain those pressures in anything larger than a millimeter scale chamber becomes rapidly impossible. It is a physics problem. We don't have materials capable of building large-scale pressure chambers at these conditions, because those materials would themselves need to be stronger than what we're trying to make. Think about what that means in practice. The equipment that generates these pressures fits in the palm of your hand. The diamond tips are smaller than a pencil eraser. You're not scaling this up by building a bigger version. There is no bigger version. It would be like trying to recreate the conditions at the center of the Earth inside a machine you could ship by FedEx. That's not an engineering challenge. That's a different category of problem entirely. There are researchers exploring lower pressure routes. Some experiments with furan have produced nano thread-like structures at around 10 gigapascals. Other precursors, including FDCA, have achieved near crystalline threads. The material is improving, the synthesis is advancing. And the assembly problem remains exactly where it was, because better threads you cannot align are still threads you cannot use. And that's before we get to the problem that makes the first two look minor. Because even if you solve production and pressure, even if someone builds a machine tomorrow that makes nano threads by the kilogram, you still can't use them. This is where everything breaks. The nano threads that come out of a diamond anvil cell are not aligned. They do not come out pointing in the same direction. They do not come out in convenient lengths. They are tangled, randomly oriented, intermixed with other carbon structures, and embedded in a matrix of material that itself needs processing. And they are too small to physically manipulate. A nanothread less than a nanometer wide is not something you can grab with any instrument we have. Think of it this way. Imagine you have 1 billion perfect carbon fibre filaments. Each one is extraordinarily strong. But instead of being aligned in a bundle that you could braid or weave into a composite material, they are scattered randomly across a surface, pointing in every direction. Tangled with each other. Some are 10 nanometers long, some are 100 nanometers long. You need to pick them up, orient them, and arrange them into a structure. Now make each filament 1,000 times thinner than a human hair, and make your tools unavailable because no tools exist at that scale that could do the job. That is the assembly problem. Two approaches have been proposed. The first is self-assembly, designing conditions under which nano threads align themselves spontaneously. There is a theoretical basis for this, but it has not been demonstrated at large scale. The second is composites, using randomly oriented nanothreads to improve the bulk properties of a matrix material, the way chopped fiberglass improves polymers. That is more plausible in the near term, but it does not exploit the full strength of the threads, and the improvement would be modest. Neither approach has closed the gap, but both are active areas of research, and the field is not standing still. Researchers have achieved ordered nanothread arrays on the scale of tens to hundreds of microns, and near crystalline threads are becoming more reproducible. The deepest problem is not alignment, it is something more fundamental. Defects matter enormously in materials science. Real steel has grain boundaries, dislocations, inclusions, structural imperfections that affect how it performs under load. Engineers account for this. They design with safety factors, they test to failure, they know the distribution of real-world performance because they have broken thousands of samples and built statistical models from the wreckage. With diamond nanothreads, we have none of that. We have theory. We have spectroscopic signatures. We have the equivalent of looking at a bridge blueprint and calculating its load capacity, without ever having built a bridge, tested a cable, or watched one fail. We don't know the defect density. We don't know how sensitive performance is to those defects. We don't know because we have never had enough material to find out. The assembly problem is not just about alignment. It is about the fact that until we can assemble these threads into testable structures, we cannot even confirm the numbers we are working from. Diamond nanothreads are not the point, or rather, they are the example, not the lesson. Carbon nanotubes were brought to widespread scientific attention in 1991. They are experimentally extraordinarily strong. Actual tensile testing of individual nanotubes has confirmed strengths in the range of tens of gigapascals, well above structural steel. They are real. Their performance is real. And yet your car does not have a carbon nanotube body. Your building does not have carbon nanotube structural members. 30 years and billions of dollars later, carbon nanotubes remain a specialty material used in tiny amounts as an additive in composites or in niche electronics applications. Assembly, purity, consistency. You cannot grow carbon nanotubes of a single type. You get a mixture of metallic and semiconducting variants, different diameters, different chiralities, all tangled together in a mat. Separating them is expensive and lossy. Aligning them is hard. Building anything macroscopic from them, where the nanostructure actually controls the bulk performance, has proven stubbornly difficult. Graphene was confirmed by Geim and Novoselov in 2004. The Nobel Prize followed in 2010. Experimental measurements put its strength around 130 gigapascals, roughly 100 times steel. Single-atom thick sheets of carbon with extraordinary conductivity, optical properties and mechanical performance. Your phone screen is probably not made of graphene. Your aircraft is not clad in graphene. After 2 decades and a research investment that makes carbon nanotubes look modest, graphene's primary commercial applications are as a small percentage additive in paints, lubricants and batteries. Why? You cannot make large defect-free graphene sheets economically. You cannot transfer them without introducing wrinkles and tears. You cannot stack them without losing properties. You cannot integrate them into manufacturing processes designed for other materials. Graphene was partially synthesized in 2022 after decades of theoretical work. It is a new carbon allotrope with predicted properties that rival graphene in some dimensions and exceed it in others. It is already being called the next graphene. It is already facing the same synthesis, purity and assembly questions that graphene faced in 2004 and has not fully answered yet. Notice the dates: carbon nanotubes 1991, graphene 2004, graphene 2022. The gap between discovery and disappointment is not getting longer. If anything, the cycle is accelerating. We are getting better and better at finding extraordinary materials. We are not getting meaningfully better at using them. The pipeline is filling faster than the other end is emptying. Each of those stories ends the same way, not with failure, with a gap between what the material is and what we can do with it. The pattern is not coincidental, and the conclusion it forces is uncomfortable. Part of what sustains the gap is structural. Discovery is fundable in a way that manufacturing is not. A paper announcing a new material with extraordinary theoretical properties generates press coverage, citations, grant applications. A paper announcing a 12% improvement in nano thread alignment throughput does not. The incentives of academic science are calibrated for the moment of discovery, for the announcement, the confirmation, the noble. What comes after that, the decade of unglamorous process engineering required to actually use what was found, falls into a different category entirely. Less prestigious, less visible, harder to publish, harder to fund. So the cycle repeats. A material is discovered. It is genuinely extraordinary. Excitement builds. Researchers move toward the next discovery. And the manufacturing problem, the hard, slow, unsexy problem, waits. The discovery era is over. That sentence would have been unthinkable 50 years ago. For most of human history, the limiting factor was imagination. We did not know what to look for or where to look. Now we know. The problem has inverted. We are no longer limited by finding materials that are strong enough, light enough, conductive enough, or thermally stable enough. We have theoretical designs for materials that exceed every structural requirement we can specify. The periodic table is fully mapped. The space of possible molecular structures is vast but increasingly navigable. The bottleneck has shifted. We are now limited by manufacturing, by the ability to take structures we can design and confirm at the nanoscale and produce them at the kilogram scale with sufficient purity, alignment and consistency to matter in the real world. This is a different kind of problem. It does not yield to the same research strategies. You cannot solve a manufacturing problem with a better theory. You cannot solve an assembly problem with a smarter simulation. These require different tools, different expertise, different investment horizons. And right now, across materials science, the manufacturing problems are lagging the discovery problems by decades. Come back to where we started. Benzene, compressed beyond imagining, transformed into something barely visible under the most sensitive instruments we have. The synthesis is confirmed. The sp3 bonding is confirmed. The structural analysis is consistent with what theory predicted. These threads have been made repeatedly by multiple research groups. And the theoretical case for their properties is genuinely compelling. The numbers, if they translate to experimental reality, describe a material that would be transformative in any structural application where weight and strength are in tension, which is nearly every application that matters. But, and this is the but that matters, production, pressure, assembly, diamond nanothreads are not failing because they are weak. They are failing because they are unusable, not permanently unusable. That distinction matters. There are research pathways that might change the synthesis picture. There are ideas about self-assembly that might one day make alignment tractable. There are composite approaches that might extract partial value from disordered nanothreads without requiring perfect alignment. The pathways exist. None of them are fast. For 200 years, the hard part was finding the right material. That era is over. Now the hard part is everything that comes after finding it. And as you encounter the next announcement of a world-changing material, the one with the astonishing theoretical strength, the Nobel-level discovery, the press release about the future being here at last, I invite you to ask a different question than the one you are used to asking. Not how strong is it, but how do you build with it? The future of materials science may not be discovering stronger materials, it may be learning how to hold the ones we already found. That is a quieter problem than discovery. It does not have a eureka moment. There is no single experiment where everything clicks and the material is suddenly useful. It is process engineering, it is manufacturing. It is the slow, expensive, collaborative work of turning something that exists in a laboratory into something that exists in the world. But it may be the most important problem in materials science right now. The gap between what we have found and what we can use is not small. It is decades wide across multiple materials with implications that touch aerospace and medicine and defense and energy and infrastructure. The materials are not the constraint anymore, we are. Diamond nanothreads might be one of those materials, or they might not. The experimental numbers might come in lower than the models predict, and some other candidate might take their place in the conversation. But the question the field is being forced to confront is the same either way. Right now, somewhere in a laboratory, there are almost certainly materials that already exist, confirmed, characterized, extraordinary, that we simply cannot use. Not because they failed, but because we have not figured out how to hold them. The next breakthrough in materials science might not be a discovery at all. It might be someone finally figuring out how to use something we already found. That's the question worth asking, not what we have yet to discover, but what are we already sitting on?